Welcome to virtual science. All right, so today we're going to look at forces and Newton's third law specifically. So Newton's third law, let's get a volunteer. Newton's third law says for every action there is an equal and opposite reaction. Okay, so first of all we want to prove that. For every action there's an equal and opposite reaction. All right, so David, this is a spring scale, and spring scales measure your force. So these are spring scales. They measure your force, okay? So basically we pull on it, so just pull that. Does that measure how hard you're pulling?
Yeah.
How much force you got?
2,000.
All right, so you, 2,000. I don't want to respect that.
There's 20 newtons. Yeah.
20 newtons, that's better. 20 newtons of force. Okay, so now David, that's 20 newtons. All right, so that measures how much you pull. This one obviously is going to measure how much Mr. Harn pulls. All right, so we're going to connect them together. And the first thing we want to prove is for every force there's an equal and opposite force. All right, this time I don't want you to pull. Don't pull, okay? Don't pull. Why are you pulling? Huh? Yeah, I'm pulling. Why is he pulling?
Because you're pulling him.
Okay, so Newton's third law is true. For every pull, there is a pull. Are you pulling?
Yeah.
I mean, you got to be pulling. Even though in your mind you're like, all right, now pull against me. Well, we just made it even greater. So even if I say don't pull, he's still pulling. Now, how much force do you pull with?
About 7.
Yeah, mine's 7 too. So not only are they equal, but they're also opposite. Come closer so the virtual kids in homeland can see this. Okay, enough of that. So Newton's third law. We just proved Newton's third law. For every force, there is an equal but opposite force or reaction. Equal but opposite force. Now, if all forces are equal, Hunter, if all forces are equal, then the system is in equilibrium. If it's in equilibrium, then the net force is 0 and the acceleration is 0. Okay? So let's show you a system that is in equilibrium. So here we have a hovercraft built by Mr. Harn. It's a hovercraft. It's got a piece of plywood with some holes cut in it. A piece of plywood with a bigger hole cut in it. All right. Chandler, you up? Did anybody bring their cranberry juice? You nobody brought their cranberry juice?
I can write it down.
All right. First of all, to ride, we're going to sit down.
Oh.
Well, let's just see how this thing works before we try to circle it. All right. All right, so, excuse me, this goes right here. Absolutely turn around like this. You'll need to scoot up. Okay, so right now we're trying to look at a system that's in equilibrium. For every force, there's an equal and opposite force. So we're going to use this leaf blower to apply force. Which way is the leaf blower going to apply force? Yeah, be careful. That's the wrong answer. What's pulling him down? Gravity. The leaf blower is going to push up. So the leaf blower goes up, the thing goes down. Somebody walk in that section of the hallway. Say something magical like falling. There you go. Go back. All right, turn the leaf blower on. Well, keep looking for it. You find it. Okay, so the leaf blower is going down. Excuse me, the leaf blower is pushing that force up. So here's the thing I want you to think about. This is why we're getting confused, right? The leaf blower is pushing down, but it also applies a force equal but opposite up. Now he's got a force of gravity going down. He's got a force of leaf blower going up. They're in equilibrium. So he's not moving up or down. He's at one spot. Now, we get to another point, notice too, is we've also lost something. Okay, so for example, let's see if this thing actually moves. Let's see what. Are we even in that screen? All right, I'm going to push you. Ready? That force doesn't work. Please decrease the amount of force. Venture out onto the island or something. Okay, so the other point I wanted to make though was, how did we make him move? Because we pushed on him and he didn't move.
You reduce the friction.
I reduced the friction. Every force, there's an equal and opposite force, but don't forget about that other force that's out there. Friction. Let's move on to the next part. We'll let somebody else get on this if you want to. It's, I mean, you know, it ain't all that, but it's probably never seen that before. But all right, so now we're gonna have a tug of war. Who wants to tug of war with Mr. Harmon? Okay, let's go. Home, did you get this?
No, you do it, Harley. Harley wants to.
You gonna tug of war?
I'll wrestle. Well, not wrestle.
You gonna jump off the top ropes or something?
What do I need?
Well, we're gonna sit on the floor.
I can check that up, bro.
Okay.
All right.
No idea.
No.
It's a thingy.
All right, so we're going to do a tug of war.
A lever.
Now, in a tug of war, that's Newton's third law. For every force, there's an equal and opposite force.
Huh?
Ohm is now trying to untangle this string for 30 minutes.
Give me scissors. I can do it right now.
No.
Bro, I literally coiled that little part. How'd you tangle it?
Why didn't you give it to me?
There is this magical thing about ropes and garden hoses. And how about ladders when you try to, little speed ladders? How do they get so tight?
Ladders?
Speed ladders.
We're
Little stringy things with things that runs on you.
not ladders. Get tangled in.
No, my ladders never got
Yeah,
tangled.
let's find this out.
Kill that for me.
Yeah.
Stop it.
Yeah, I guess so.